Welcome to Construction Math. Today we're going to look at the beginnings of linear programming and constraints. So on your note taker, I need you to write down a time you needed to optimize something. So think about it for a minute and then write it down. But if you're not familiar with the term optimize, or it's been a while since you heard it, it means to make the best or most effective use of something, like a situation, an opportunity, a resource. So list it on your note taker, share with your partner. Teacher, pause the video and call on non-volunteers, and I'll meet you back here in a minute. Welcome back. Now, the objectives for today. So on your note taker, fill in the missing terms that are in red. Number one, we're going to define terminology. Number two, we're going to list the steps in linear programming. Number three, given a graph of constraints, we're going to find the vertices of a feasible region. And don't worry if you don't know some of these terms, because 4 of these terms are our vocabulary for today. And then we're either going to compute the maximum or minimum of an objective function. All right, so teacher, pause the video until students have had a chance to look at those and copy them down. Now, our bell work for today, our math check, is to be able to match the equations or inequalities with the graphs. So teacher, pause the video until students have had a chance to complete them, have them share with their partners, and I'll meet you back here in a minute. Welcome back. Let's look at what these say. All right, since we already have the graphs drawn, I want to share with you. Number 1 and number 2 are both inequalities, so they're going to have a shaded region. All right, so if I'm going to graph y equals to 1, it's a horizontal line, and greater than means everything above that line. So number 1 would be C. Number 2 again is an inequality. If I solved it for y, I would get y is less than negative x plus 3. So the y-intercept would be at positive 3 and its slope would be negative 1. So that matches with the graph for A. Number 3 is a line. It's just an equal sign. If I solve it for y, I get y equals negative x plus 1. And I think the graph is incorrect. It should have been above the line by 1. So I'm going to fix it later, but just so that you know, number 3 should be B if it was raised up 2 units. All right. And there we go. We've checked them out. Now, terminology. You're going to have 4 different ones, and so I'm going to go through. Your teacher may pause at any time. So linear programming is what we're going to do today, and it's a mathematical technique for maximizing or minimizing things that businesses need to do or anybody that has materials. It's going to minimize or maximize a linear function of several variables such as output or cost. It has nothing to do with computer programming. This term was around a lot before we ever, in the dark ages back in the 60s and 70s, did computer programming. So complete the vocabulary square, and teacher, have the students share their meaningful sentence. And I'll go on with the next one. The next one is constraints. What constraints are? Restrictions or limitations. For example, if I wanted to sell things in my store, I couldn't sell necessarily 1 million items if there wasn't room to store them or if I didn't have the funds to buy them. So it's things that make physical sense. Also, there is nothing like having negative time. I can't sell a negative number of cars. So constraints are things that are restrictions. Again, complete the vocabulary square. The next term is objective function, and it's the function or the equation we use to optimize a value in linear programming problem. Most often, the variable used for a objective function is the variable z. Most often you'll see z equals. Again, complete the vocabulary square. And feasible region. That's when we graph several inequalities, and it's the overlapping region. It's an area of intersection that satisfies all the constraints, not complaints, constraints in a linear programming problem. So teacher, have the students pause, fill out their vocabulary squares, and I'll meet you back here in a minute. Welcome back. Now, these are 2 terms you need to become familiar with. the greater than or equal to, the less than or equal to, as it's translated into English. So fill in on your note taker anything in red. The term or the phrase at least means that that number is the smallest number possible, and it translates in math into a greater than or equal to sign. At most means that the number is the greatest possible number, so it translates into less than or equal to. Those are two things that you're just going to need to remember, and hopefully it makes sense to you. So let's go on. I want you to work and think pair share with your partner to come up with a way you're going to remember at least and at most. Teacher, pause the video, have students share with another group, and then call on non-volunteers. And I'll meet you back here in a minute. Welcome back. All right, we have 3 examples. A number is at most 3, a number is at least 7, and the sum of 2 numbers is at least 3. So what I need you to do is translate this from these English sentences into a math sentence. Pause the video, and I'll meet you back here in a minute. Welcome back. Let's go to our slates and let's look at this. All right, first of all, it says a number is at least, is at most and 3. So here we go. I'm going to translate a number into any variable you want. I'll pick X. Is at most means less than or equal to, and 3. It means the number can be 3 or any number smaller than 3. The next sentence says a number is at least 7. So again, a number, any variable you want. I'll do Y. Is at least. At least means greater than or equal to, and then we put in the 7. That means the number is at least 7 or bigger than 7. The last sentence says the sum of 2 numbers is at least 3. Again, the sum means addition. We have 2 different numbers, so I'm going to pick an A and a B. You can pick an X and a Y if you want to. Is at least means less than or equal to, is at least should have been greater than or equal to, and then 3. And there's our answers. So again, be very careful because I started to misread it, and I don't want you to do that either. So let's clear this off once your students are finished, and we'll go back to our PowerPoint. Let's go ahead and see. Oh, we got them all right once I caught my mistake. Now, here's an example. A carpenter does 2 kinds of services, repairs and framing. It takes 4 hours to do an average repair job and 2 hours to do a framing job. The mechanic can the carpenter can spend no more than 32 hours per week working and must do at least 2 repair jobs and at least 4 framing jobs each week. He makes a profit of $35 on a repair job and $20 on a framing job. How many of each should he do to maximize his profit, and what's his profit? So I'm going to teach you the steps to be able to solve a problem like this. All you need to do right now is fill in the missing numbers that are in red and also change it from the mechanic to the carpenter. And teacher, pause the video until everybody's had a chance to do that on our note taker. Welcome back. Let's look at the steps. First of all, you're going to create and graph the inequalities. That's what we did in the last lesson, was learn how to graph inequalities. Then we're going to find the vertices of the feasible region or the shaded region, and vertices are the corners. So we're going to find the ordered pairs that name the corners. Number 3, we're going to compute the objective function at the vertices, and depending on, for number 4, what the problem asks us, we're either going to find the largest value if we want a maximum or the smallest value if we want a minimum. So fill in the missing terms in red on your note taker. All right, now we're going to do an A-B partner teach. So we're going to have you guys work partner A and B to teach each other the steps. All right, Teacher, pause the video and let them work on it because we're going to have a little quiz in a minute. Welcome back. So on your slates, I'm going to ask you to put these in the correct order by writing the letter. So here we go. Which one goes first, second, third, and fourth? So teacher, pause the video. When the students have finished, prompt them to show you their slates. And I'll meet you back here in a minute. All right, looking at those, step number 1 should be D, create and graph the inequalities. We've got to get the picture first. Step number 2 is B. Once we have the graph, we want to find the vertices. Then the next thing is, for A, we're going to compute the objective function at the vertices, and then C, we're going to be able to find either the maximum or minimum value depending on what the problem was asking us. So let's go on. We've got the answers there. Now, here's what it looks like in math. I'm going to take out the word problem and just go right to the constraints. You're going to have an objective function. It says z equals 3x plus 2y. It may be something like profit, that on item X you make $3 profit, on item Y you make $2 profit. We have the constraints, x is greater than or equal to 0, y is greater than or equal to 0. Those are normal constraints unless something in the problem tells you it has to be larger, because in real life problems we don't often get anything that could be negative. Then we're going to graph x plus 2y is less than or equal to 4, and x minus y is less than or equal to 1. We're going to graph the constraints and find the vertices. All right, so what I'm going to do is I'm going to go to my slate and I'm going to look at this. Because x is greater than or equal to 0 and y is greater than or equal to 0, I really only have to graph in quadrant 1. Everything I shade is going to be in quadrant 1, because remember, quadrant 1 is x is positive, y is positive. Quadrant 2, x is negative and y is positive. Don't want that. In quadrant 3, x is negative and y is negative. Don't want that. And in quadrant 4, x is positive and y is negative. I don't want that. So it's going to be in this quadrant right here. And so I've graphed x is greater than or equal to 0 and y is greater than or equal to 0. That's why my final answer can be up here. The next equation was x plus 2y was less than or equal to 4. Remember to graph, I want to solve it for y. So I'm going to subtract x from both sides. I'm going to divide everything by 2. Remember, multiplying and dividing by a negative flips the inequality, but I divided by a positive 2. So I'm going to graph y is less than or equal to negative 1/2 x plus 2. All right, and here's the y-intercept. So I go up to positive 2 and put a dot. Its slope is negative 1/2. So from there I go down 1 and right 1. I'm going to draw the graph, and it's going to be a solid graph because it's less than or equal to. So it's going to come like here, and it's going to be everything below that graph because it's less than. The next equation said x minus y is greater than or, is less than or equal to 1. So I'm going to again solve it for y. So I get negative y is less than or equal to negative x plus 1. Divide everybody by a negative. And remember, when I divide by a negative, it's going to flip. So y is greater than or equal to negative x minus 1. Now when I graph this, I know the y-intercept's negative 1, and its slope is negative 1. Down 1, right 1. Or is that, should that be positive? Oh, I'm sorry, should be a positive. So from there, I'm going to go up 1 and right 1. And then this again is a solid line. Oops, I'll make the dot a little bit bigger. And it says it's everything greater, so it's everything this way. And it's got to be greater than y and greater than x. So it's everything in this quadrant, and it's got to be lower than that, but greater than here. So it's everything in this little four-sided figure right here. So we're going to shade that in. And then we're going to find the vertices. All right, this one's pretty easy because he's on an axis. That's the point 0, 2. This point is the origin. He's 0, 0. And then this point is 1, 0. And then this point, I'm going to look at my better graph, and I'm going to find out that that point is going to be the point 2, 1. And I had it on graph paper so I can tell. So now I've got all of the vertices, and that's what I needed to have happen. Those are steps. That's step 1 and step 2 that we're going to do that for. All right. Now, I'm going to save that, and I'm going to go over here, and I'm going to write my objective function. It was c equals 3x plus 2y. And what I need to do here is I need to put in each one of these 4 values and compute it. So I'm going to go z equals 3 times 0 plus 2 times 0. That gives me an answer of 0. The next one is the point 0, 2. So it's 3 times 0 plus 2 times 2. Remember order of operation, I do multiplication first. 3 times 0 is 0, 2 times 2 is 4, 0 plus 4 is 4. I do the next one, 2, 1, 3 times 2 plus 2 times 1. Again, remembering to do the multiplication first. 3 times 2 is 6, 2 times 1 is 2, 6 plus 2 is 8. And the last one is the point 1, 0. 3 times 1 is 3, 2 times 0 is 0, so I get a total of 3. Now I look back at the problem. The problem wanted me to maximize. So I'm going to look down my answers and find the one that's bigger. 0 is the first one, 4 is bigger than that, 8 is bigger than 4, but 3 is not. Here's my answer. So the maximum is 8, and it occurs at the point 2, 1. And that's my answer. Now, in a real life problem like the one that we did before, you would say that the maximum would be like $8 profit, and it occurred when you had 2 jobs repairing something and 1 job manufacturing something or maintaining something. But that's how we work our problem. So teacher, pause the video and have the students answer any questions that they might have. You can help them or other students can help them. Welcome back. Let's go on back to our PowerPoint. And here's the feasible region. And we have our vertices. We found the answer. Oh, I did it right. Now here's a you try. In this particular lesson, you're never going to have to probably do a whole lot of graphing for yourself or translating word problems. That'll come next year. So here in this one, here's a you try. And I want you to, we've got the graph, so I want you to find the vertices and maximize the objective function. Teacher, pause the video, have the students work the problem, and then call on non-volunteers, and I'll meet you back here in a minute. Welcome back. Let's go to our slates. And I got the vertices off of my graph. In no particular order, I have the graph point 0,3, the graph point 0,5 is a vertice, and the last one is the point 3,2. The objective function, z was equal to 3x plus 4y. So let's make that a 3x plus 4y. So now all we do is substitute in. When x is 0, y is 3. I'm going to do the math. 3 times 0 is 0. 4 times 3 is 12. 0 plus 12 is 12. Let's do this one. We get 3 times 0 plus 4 times 5. I get 0 here. I get 20 here. 0 plus 20 is 20. Here, I'm going to get 3 times 3 plus 4 times 3. I get 3 times 3 is 9. 4 plus, oh, this should have been a 2. So 3 times 3 is 9, 4 plus 2 is 8, that's 17. So here is our maximum value. And it occurred at the point 0,5. If it wanted a minimum value, this would be the minimum value, and it would have occurred at the point 0,3. And so our maximum value was 20. All right, pause the video if you need to. Welcome back. Let's go back to our PowerPoint. And let's go on. There, we checked it. And then here's your closure. We have a 3, 2, 1 closure. Write down 3 important terms we talked about today. We have 2 ideas or facts you'd like to know more about, and 1 skill or concept that you've mastered. And next year we should be able to have another video on further linear programming.